welcome to part 3 of further mathematical induction, where we're looking at series and sigma notation. We're going to do part 3 in 2 videos. The first video where we'll have a little look at sigma notation and a bit of an introduction, and then in the second video we'll do an induction question that involves sigma notation. Alright, let's get into it. We've seen this guy before. This is the sigma. It's a Greek letter and it's often used to represent a sum. Well, in what we're looking at, a series is just a sum of certain terms. So when we write a series out, we start with our first term, term 1, and then because it's a sum, so we're adding, we go on to our second term, and so on, keep adding all the way until we get near our end. So if we call our nth term the final one, then the second last term will be t of n minus 1, and then our last or our nth is tn. So that is our series. But we can use sigma notation to condense this and write it a little bit differently. So we have our sigma here, the sum of, and then we have our t for term, and in this case we have like a dummy variable k that can take on any value that we like. So we tell it where to start, so in this case we're starting at 1, so k equals 1, and then we go all the way up until our end, which in this case is n. So we put the ending value up here. And so this is just a, like I said before, a nice compact way to write this entire series here. Alright, let's do some examples to understand sigma notation a little bit better. So, example 1. Evaluate the following sum from k equals 3 to 6, 1 on 3 to the power of k minus 2. So each one of our terms is going to be of this form. So let's start by writing out the question in sigma notation. Okay, so we're going from 3 to 6. Each term will be in this form. Now, to evaluate means we're going to actually work out a numerical answer to this series, to this sum. Let's start with the first term when k equals 3. So you have 3 to the power of 3 minus 2. Second term when k equals 4, and so on. So we've got 5 and 6. See if we can fit them all in. Easy. Alright, so 4 terms all up, right? And that's something, we can see that quite clearly here. 3, 4, 5 and 6. Let's fill these in. But just something to be aware of. It's an easy mistake to make, to think that there's only going to be 3 terms, because we're going from 3 to 6, but they're both inclusive, right? So the number of terms will be the difference between these two numbers plus 1. Right, so 3, 4, 5, 6, 4 terms. Alright, let's simplify each of these terms a little bit. So we've got 3 minus 2 is 1, so this is just 1/3. Then we've got 1 on 3 squared, 1 on 3 cubed, and finally our last term is 1 on 3 to the power of 4. Now we're evaluating this expression, so let's evaluate each of these. 1/3 plus 1/9 plus 1/27 plus 1 on 81. Okay, and all we have to do is add these 4 fractions to get our final answer. Use the calculator. 40 over 81 is our final answer. Alright, let's do one more example. Now, when I said one more example, it's got 2 parts within it. Sorry. Okay, so part A, we've got to express this series here, this sum, using sigma notation. So what do we notice first? Well, each term is squared. Okay, so we can see the common link there. However, we should also notice that the sign flips from a positive term to a negative second term, and then back to positive, and so on. So we'll deal with that in a minute, but if we were just to focus on this series as if it were all positive, what would that look like? Okay, so everything is positive. Let's just focus on this for a second. I know it's not the original question, but how would we express this using sigma notation? Well, it's a sum, so we draw our sigma. Where are we going from? We're going from 1 at the lowest to 100 at the end, the highest. So we put in our dummy variable, we use k. We're going from 1 to 100, and then each term is of the form k squared. So 1 squared, 2 squared, 3 squared, all the way up to the 100th term, 100 squared. So if that was the question, that would be our answer using sigma notation. But now let's try and account for this switching, negative, positive, negative, positive. So what are we going to do to account for that? See, the magnitude doesn't change when we look at each term compared in both lines. The magnitude doesn't change, just the sign. So because the magnitude doesn't change, we want to multiply by 1 essentially. But because the sign changes, we need to introduce negative 1. But we can't just multiply everything here in the green row by negative 1, because that would switch it all to negative. So we need this alternating pattern. That's where we can use powers. If we raise negative 1 to a power, for the even powers, we will get plus 1, right? Think of negative 1 squared, for example. And for the odd powers, we'll get minus 1. But we don't just want to introduce yet another dummy variable. We want this n to relate somehow to the k. So let's think about it. In our first term, so when k equals 1, we want the whole term to be positive. Now remember, positive terms come from an n value being even. But k equals 1 in our first term, which is odd. So we can't just make this k, because that would flip the sign on every single term. So we need to adjust the power 1 either side of k. So that actually gives us 2 options. Right? When we could either subtract or add 1. So this negative 1 to the power, we want the very first term, we want this power to be even. So we could take k, but then we could either plus or minus 1. It doesn't matter. See, when we focus on this first term, when k equals 1, we would get 1 plus 1 is 2, and minus 1 squared is just 1, and so we get our positive first term. But then on our second term, when k equals 2, we will get 2 plus 1, which is 3, and negative 1 to the power of 3 gives us negative 1, and so we get our negative, which is what we want. Okay, like I said, we could express this as minus 1 to the power of k minus 1 if we wanted as well. That does the same thing, because in our first term, when k equals 1 and we get 1 take away 1, that's negative 1 to the power of 0, and anything to the power of 0 is just 1. So that gives us what we would want as well. And then we get the alternating pattern as we go forward. So either of these are acceptable. Okay, part B. We have 1 over 1 times 2 plus 1 over 2 times 3 plus 1 over 3 times 4, and then it just continues off with no final term given. So let's address that first. That's telling us that this is a series or a sum that goes to infinity. So when we write in our endpoint for our sigma notation, it's just going to be infinity. But how do we start? Well, we want to start with the first term. Now we can see that this 1 over is common. Put that in. So each term has 1 over, and we want to start at 1. But what is the link on the bottom here? If that is our k value, how would we describe this value in relation to k? Well, we can see that along the bottom here, this number, this second number, is always 1 more than the first number. So 2 is 1 more than 1, 3 is 1 more than 2, and 4 is 1 more than 3. So if we have our k value here, then the number it's multiplied by is just 1 more, k plus 1. And that matches the pattern that we see. So when k equals 2, we have 2 times 3. And in our third term, when k equals 3, we have 3 times 4. And that's the answer for our second one. So a little bit nicer without that alternating plus minus plus minus. In the next video, we'll put some of these skills into practice with an induction question.